facial issues is this person going to have?
Weird facial issue?
Yeah.
So this is 8 people, so.
So he has 8 faces then.
I
Okay.
mean, yeah, there's something strange. Yeah, I don't think I have any reminders or anything. This is the big list we're working our way through. We already talked about Fairmont. And the fight between Newton and Leibniz. I was sort of surprised to find out that in the Bernoulli family there's lots of good fights too, so we'll get to talk about their interfamilial warfare. Those are what we wanted to talk about today.
Game of Thrones, but more boring.
I picked Bernoulli number 3.
There's a couple of them
You
that
said
are the
there-
third of their name.
You said there was 8. You said there was 8. I picked the third one to
Oh,
talk
okay.
about.
That was a picture of Vermont. I just messed up.
Whoever the third
That
one
was the wrong
was
picture.
Upsetting.
So you
I
all the
forgot to
prime,
edit the thing. Sorry.
all the prime Bernoullis. So 2, 3, 5, and 7.
What about one?
That's not prime.
I know, but shouldn't we talk about one? The units are the primes.
Nope, no, it's not prime.
You're both wrong. I think the best one.
The best one. Yeah, that's a hard one. That's really a hard one to say. So, I mean, this family produced not just a lot of mathematicians, but a lot of really amazing mathematicians. They did some incredible stuff. In fact, okay, so have you ever heard this concept, the math gene? Some people have the math gene, and other people just don't. I think it's an excuse a lot of people take because they don't feel like they're good at math. They don't want to study it, and they go, "Well, I just don't have the gene, so it's cool." But I don't think that's true. I think human beings all have the ability to think about quantitative stuff and reason with it, with mathematical methods. But there is something going on. I mean, there must be some kind of.
I think everybody has the ability, but I definitely think some people's brains are wired more towards one
Yeah,
particular way.
so it's not like it's not binary. You either have it or you don't.
No.
And these guys like
It's
had
a
a special
scale.
version.
Math is a spectrum.
Yeah, there you go.
I'm on the spectrum. I'm on the All right, so yeah, that's the classic nature versus nurture debate, right? Because it could have been just the way these people were raised, which is also something that you pass down to your children. You raise your children often the way your parents raised you, right? That may have had the influence that caused them to all become mathematicians. Strangely, here's another comment on raising your children. Several times during reading the biographies of these various Bernoullis, they say things like, well, his father insisted that he go study theology, so he took up math on the side. They were being forced to do something other than mathematics, which is an excellent way to get a child to do the other thing. Right? If you ever have children, you would want to remember this. Tell them to do X, and you'll get them to do Y. So you just try to. It's like leading a pig. Have you ever seen how people lead a pig? You take a switch, right, and you hit it on the side you want it to turn towards. It goes. It's most. You think intelligent animals would go away from the pain, but they don't. They like try to move in the direction of the pain to fly. Kids are like that too. They go the opposite way you expect. Anyway, there's a link here. Whoops, I've done the wrong thing and made the. I don't think I can select this. Okay. I come out of that? No, still not.
Can you just click it?
See what I did is interchanged the target name with the URL, so I've got the backwards. That's why we're seeing the URL here. So I guess I'm just going to do the same Google search that I did here before, and we'll find it. It was for the Bernoulli family tree. Okay, so first a little bit about their names. There were, I guess there's only 4 names amongst these 8 people. So a lot of them will have Roman numerals after I'm telling you which, Daniel or which Nicholas they were. But there also are multiple languages that their names appear in. So it can really be confusing sorting out who's who. The family was originally from Belgium. And so at that time, Belgium was taken over by Spain. And the King of Spain sent an army to Belgium to enforce that everybody should follow the Catholic faith and stop protesting that the Spaniards ruled the place. And these Bernoullis were Protestants, so they had to get out. I mean, there was a death order for people who, there was something like 12,000 people had warrants out to be arrested and killed. And so they fled Belgium, and these people went all over the place. The Bernoullis ended up going to Switzerland, and they became prominent members of the town of Basel. What do I say wrong? Basil, like the spice, like the, not basil. I think basil is the spice and basil is the thyme. Anyway, so in that area, so you got to know a little something about Switzerland here. They have 3 official languages in Switzerland. They're in the mountains right in between Germany, France, and Italy, so they've got German, French, and Italian as languages. And different parts of Switzerland have each of those languages. Plus, there's another thing called Schweizerdeutsch, which is a sort of a dialect of German they speak in parts of Switzerland. So yeah, that's why they would have had French versions and German versions of their names. The Italian versions would have probably been pretty much the same as these Latin versions, but they didn't use them because Basil's in the German speaking part.
Daniel lucked out there.
Sorry?
So Daniel lucked out there.
Yeah, Daniel's just Daniel. That's actually a Hebrew name. Right? You know Daniel from the Bible?
So is Johann, is that the same name as Gohan?
No.
Gohan?
Gohan?
No.
Who's Gohan?
It's
Just ignore him. Just ignore
it's a
him.
TV show reference.
Ah, television. I've heard of that. So yeah, I'm gonna probably stick with the German versions of the names.
Sweet Johann.
Jakob.
Jakob?
These J's are pronounced like Y's, by the way. So that's Jakob, Johann, Daniel, and Nicholas. Not Nicholas. I would have said the A's version of it. So that's their names, and then this is the family tree. Where are the mathematicians in here? Because this is not everybody. So Nicholas is the granddaddy of them all, but he was a spice dealer. He was a businessman. So he left Belgium and set up shop in Basel.
So he sold basil and basil.
I don't think he sold basil, but I believe he sold other spices. This was like he owned a shipping company, is more of the way to put it. They sent ships out to India and got the cardamom and cinnamon and all those kinds of spices.
Okay.
Probably not nutmeg, right? Because that was discovered after. No, maybe nutmeg. Because that's a New World spice.
No, it's from Indonesia.
Oh, I thought it was grown in Aruba.
Maybe
So this is my history of Connecticut is really weak, but I understood where the nutmeg stayed because they traded us for Aruba, where they were growing nutmeg.
So why don't we be the Aruba state?
Then they would call us the hazelnut state.
So why aren't we the Aruba state then?
Yeah, we could be. Have you ever been to Aruba?
Yeah, why would anyone
Very
trade?
nice.
Who would want to trade away Aruba for Connecticut?
Well, Connecticut had a serious good farmland going on. It was, colonial times, pre-colonial times. Anyway, yeah, whatever. Lots of spices, I'm sure, all kinds of different things, but likely not basil, because that's something you grow and use fresh, right? This is dried spices. So he's not the mathematician, but all 3 of these guys are. I don't know who Hieronymus is. But I think I would like to. Wouldn't it be cool to say you have your weird uncle Hieronymus over there? Just something like that's a great name. Anyway, there's an artist named Hieronymus Bosch. Have you seen the works of Hieronymus Bosch? most famous for a painting that shows hell. So you see all the people in hell being tormented by demons, and it's a little bit obscene, but it's definitely disturbing. Anyway. So, yeah, the first Johann and his younger brother Jakob were probably the most prominent ones in that generation, in the first layer below there. Paterfamilias. Where are the rest of them? Well, there's Johann II and Daniel, these two sons of Johann I. Nicholas II, also pretty good. I don't know. Probably, well, because they probably had enough money to go around. Wait a minute. Maybe in birth order. That would make sense. Which number goes on in some place. Actually, your question originally, I was thinking you were asking about like inheritance money, but you know, which number on the, yeah. I'm trying to find the ones that have all the same name.
Nicholases don't exactly match up. You got more Nicholases than you got numbers.
Well, there's an unnumbered Nicholas who's not the guy at the top, right? And then there's 1, 2, and
So are the numbered
3.
ones the mathematicians?
And that's somebody else's. Yeah, but I don't think any of these are mathematicians. Okay, so which ones are we going to talk about today? I'm not going to get through all 8 of these guys, obviously. But we do want to make sure we talk about Johann and Jakob and Johann's son Daniel. Those are the big 3 that I want to make sure we get to them. I think I have slides on the 4th one. So go back to this. So what these guys basically took the tools that were available to and went nuts with it. They were the first people to seriously look at Leibniz's work on calculus. By the time they were working on this, a lot of people were trying to get themselves through Newton's work on calculus, on what we call functions. But Newton's writing, was obscure. It was hard to follow. Leibniz's methods were much clearer, so they had much greater success in figuring out what was going on with calculus and following Leibniz. And then, by the way, that made them prominent supporters on the Leibniz side versus Newton's side. This is a quote from a historian named Hoffman about what Jakob did. He greatly advanced algebra, infinitesimal calculus, and differential calculus. The calculus of variations, which is something you haven't studied yet, but it's the kind of thing where instead of thinking about optimizing where you find the good spots on a function, it's optimizing where you find the function that does something good. Okay, so there's a little bit of a different take on it. Okay? But mechanics, like the way machinery works, that kind of stuff. The theory of infinite series. So yeah, this is really the launching point for modern math, I would say. When people stop thinking about functions as just all functions are polynomials, right? Now, you can have infinite polynomials that went on forever, and then you get really interesting stuff like sine and cosine, tangent, and the x, and all these other transcendental functions that we work with now. And the theory of probability. But personally, look at this description. Self-willed, obstinate, aggressive, vindictive, beset by feelings of inferiority, and yet firmly convinced of his own abilities. With these characteristics, he necessarily had to collide with his similar discouragement. So he had a younger brother who, he's the one who taught math to him. He's Jakob, and he had this younger brother, Johann. Johann had been assigned by his dad to become a medical doctor. And so he was studying medicine, didn't really enjoy it that much. But he went to his older brother who was doing math and got into teaching calculus, and they worked together at first. But no, they never spoke to each other again to the end of their days. And, They got in some silly disagreement about the math they were working on, basically about who did what, and who got the credit. So that's that. A couple of accomplishments to point out for Yakov here before we leave him. You may have heard of this one if you take a probability, the law of large numbers.
We just learned about that like this week.
Can you describe it? Probability is not my thing. But I would say it's basically saying if you've got enough trials, anything weird will happen.
Being weird will happen, it'll be normal.
The bigger your sample size, like the mean of the sample size becomes closer to the mean of the population.
Okay, so that's saying if you make the sample
Big.
so you've got a
There's just
giant
become more
population,
accurate.
think of it as infinite, right?
Yeah.
And then you take a sample that's small, you don't know that it's mean and the population's mean or agree at all. But if you make the sample bigger and bigger and bigger,
You get closer to the truth.
okay, that's good. That's what he did. And then the isochrone, which I do know what that is. Hey, it's a little bit it's maybe a little counterintuitive, but let me see if I can set it up. Do you remember the thing of the artisticone problem I told you about a little while ago? This is sort of related, but not quite. The idea is to have, again, a wire or some kind of track that little bars or beads can follow. And the beads slide on the wire frictionlessly, certainly. If I let go of a bead right here, it's not going to start accelerating very much because it's on the not so slanted part of the curve. Whereas if I let go of a bead way up here, it'll begin accelerating rapidly. Right? So the idea is this, and this is a calculus of variations thing. Set up the shape of the curve so that the time that this one takes, time one, and the time that this one takes, which is traveling a much shorter distance, but time two, these guys should be equal. Does that make sense? So the point is to determine the shape of this curve so that no matter where you release the bead, it takes the same amount of time to reach the bottom. The bottom is right now. And you see how that's conceivable because you can make the ones that have a farther distance to go faster because they get accelerated. Okay. So what is the actual shape of that? I think it's a hypocycloid, actually, but I'm not actually clear on it. In any case, that was the idea, to find a curve that would have this property. That time to travel to the bottom was invariant. It didn't matter where you started, just the shape of the curve does. And so that's the isochrone. And he posed the problem first, and then he solved it. And nobody else could solve it, so that was kind of a big deal. What else? Oh yeah, Johann.
So the heart.
And L'Hopital.
So Johann is responsible.
L'Hopital. That O with a circumflex accent over it is translated into English as OS. So that literally is hospital. Okay. I mean, if you translate it into standard English characters, it's hospital. But it's pronounced L'Hopital. The L is indicative of minor nobility. Well, so L'Hopital was wealthy. He was a noble. Count. I didn't check on that. I should have probably.
Since it's a mathematician, he should be count.
Well, he was not a great mathematician. Okay, but he was interested. And again, this Johann, having worked with his brother on understanding Leibniz's work, knew calculus. And L'Hopital was looking around for somebody to be the tutor and help him learn calculus. So he hooked up with Johann Bernoulli, and they did a correspondence course, essentially. Bernoulli would write down lessons about the calculus and he'd send them to L'Hopital. And so L'Hopital eventually learned, he learned calculus probably as well as we know it. He wasn't an amazing guy, but he had a lot of leisure time, and for some reason he was interested in mastering this topic, so he did it. Then he said to Bernoulli, I'd like to write a book on this so that other people can learn this stuff. And I want to pay you to send me notes, and then I'll put it together into a book. But one condition of this is you've got to stay silent. This is my book. I'm paying you for your work. And, right? So L'Hopital did this, and Bernoulli couldn't stand it. You know, he chafed under this agreement. That he had made an agreement with L'Hopital that he would not try to take credit for their, it's really joint work. I would say L'Hopital contributed very nearly as much as Bernoulli did to the project. For instance, they finally found in like the 1920s, they found the notes that Bernoulli had sent to L'Hopital, and there were mistakes in them, which L'Hopital had fixed. So this calculus book that L'Hopital created ended up being sort of the text that people used. It's sort of like what we call Stewart today. It's the one that everybody uses. We use Stewart here. Stewart is a pretty famous calculus text. We don't use it. So, yeah, but there are a couple like that are sort of the ones that everybody uses in any given period of time. Stewart has been this elsewhere for quite a while. It's got a picture of a violin on the front. Because the guy's a huge music aficionado. Yeah, what's the name of those? Awful. Yeah. It's not as good as Stewart, actually, but it's arranged in a way that works with, we're trying to parallel the structure of the calculus course. Going to have intertransferability. Anyway, so the story is that despite being handsomely paid for this work, Bernoulli doesn't really like it. So after L'Hopital died, he said, "Yeah, I wrote that book. It wasn't him really, you know, because he agreed to silence, but up to the point that I died, and nobody believed him. It was much later when people went, "Oh wow, it looks like you really did." But still, I think L'Hopital gets a little bit of credit. And so everybody knows L'Hopital's rule?
So wait, so is it really not L'Hopital? Can I just start saying Johann? Or Gohan? Instead of, huh?
You just don't like to say L'Hopital?
I mean, well, if Johann did it, I want to give Gohan credit.
Well,
He did half of it.
Johann definitely was the one who discovered what we call L'Hopital's rule.
So it's,
But everybody else is going to think you're nuts if you start calling it Johann's rule. They're like,
I don't care. I'll start talking about this.
We already think he's nuts. What's
Oh, good voice.
voice?
So that's an interesting tidbit from the history, I think. He's the one who proposed that brachistochrone problem, and guess you know the names of two people who solved it. Not L'Hopital. L'Hopital was a second rate. He was able to communicate math well, but he wasn't.
Daniel?
Actually, the older brother, Yerko, solved it, and Leibniz himself solved it. Because that was Newton didn't so much. I thought that it was Newton that got this thing. He's not the one who got it.
So Leibniz and Newton
I
are
was
still
like,
alive.
I thought you
That's
said-
cool.
Yeah, this is early 1700s. So both of them were alive. Although they're getting older now. So yeah, that I loved it. See, this guy is the chair of mathematics at the University of Basel, right? One of the biggest seats of learning in the age. And he did so much stuff that people call him the Archimedes of his age. That's a compliment, you know. So that gives you a sense of what his accomplishments were. But he was, again, a pretty vain and disgruntled person like his brother. I think it's the way these parents raised him. It turned them into mathematicians, but it left them very sour. Maybe it was the math that turned him sour. I hope not. So he had that put on his tombstone. You know, that's reaching a little bit when you have that on your tombstone. You'd like to think people call him that. Okay, so then Johann has this one son, Daniel, and they both studied hydrodynamics, the effect of liquids working on solid objects under pressure. And so Daniel wrote a book called Hydrodynamica, and Johann wrote a book called Hydraulica. And then Johann, this is like the biggest dick move of all time, I think. Well, maybe there's others, but this, I'm not going to go with Hitler and level stuff, but this is pretty nasty. He goes, I'm gonna change the date on my book and make sure it came out before my son's. So he tried to beat his own kid in a priority debate about and they had talked together about hydraulics. So, there was some collaboration there. And then he predates his own manuscript about the thing to make it look like he'd done it all and his son had just been, a piker that came along later.
How were they able to do this without? Was I invented yet? How were they able to do fluid dynamics without I?
Well, let's see. I was definitely invented. But I'm curious about your claim of doing fluid dynamics without I.
Because I think that I is something that's really useful in fluid dynamics, or maybe at least one concept.
I think you're thinking
The
about.
Bernoulli principle.
Yeah, that's those guys.
I just now saw the connection. Yeah.
So there is a thing where you think motion of a fluid is a vector. Right? Every particle in the fluid is moving, so you have a direction that it's going and a length, and those can be translated into complex numbers. And then there is actually a complex analytic function that gives you complex numbers that move around any object you want. So if you want to, for instance, when engineers want to figure out what's the airflow around a wing, they draw the wing on the plane, in the complex plane, right? And then they produce this complex analytic function. The thing that kind of works like the limits that are the initial values in a differential equation is that way off to the left, the air is all moving this way, right? Then it interacts with the wing and it does whatever, but then way off to the right, it's all moving this way again. So you have sort of limiting value of these complex value functions off to the ends, and then you do what's called I don't remember the name for this. Well, anyway, you come up with a complex function that satisfies these things, and it's all constant over here, and does the right thing at the boundary, which usually goes to zero, right? There's a phenomenon called skin friction, so the wind that's moving near an airfoil like that is going slower the closer it gets to the surface of the thing. Now, in reality, it never goes to zero, but for a calculation, you can just say it goes to zero when you reach the skin of the airfoil. So there is that complex analytic functions approach to hydrodynamics. But I don't know if those guys did that. So I think for practically speaking, they were much more interested in ships, so incompressible flow. Water, not air. But those are both hydraulic issues. So yeah, they had a big battle. The son actually tried to patch things up with his dad. The preface of his book is honoring his father. His father was a jerk. Anyway, so Daniel, his first job, and after he got his PhD and got posted somewhere, was to go to St. Petersburg. It's Russia. You know what the climate's like around St. Petersburg?
Snow.
It snows like in June, right? And it's just awful. You're on the tundra. St. Petersburg was what stopped the Nazis from taking over the world. Right? They tried to go to Russia and take that, and they couldn't start their tanks in the morning because the oil had frozen inside the engines. Imagine these Nazi soldiers had to go out and build fires underneath their tanks to re-liquefy the oil in their crankcases so they could start them up. It was just miserable. And the men died because it was freaking cold. Anyway, Nicholas was not terribly happy. I'm sorry, Daniel was not terribly happy in St. Petersburg. He'd gone there with his own brother, with younger Nicholas, and that Nicholas died while they were there. The place was just not a nice area. So, but things started looking up because his dad sent him, after the son died, his father sent this guy named Leonard Euler to St. Petersburg. So I guess to kind of replace Nicholas Lewis.
The same Euler had the great religious method.
And about 19 other things. This, in my opinion, Leonard Euler is the best mathematician of all time. Archimedes, maybe. Euler's definitely in that category. There's maybe Gauss. I mean, some people have a different ideas about what makes the best, but Euler contributed to so many areas, and he created whole new areas of mathematics that nobody had even thought about before. So in my opinion, he's the king of us all. Anyway, so Euler goes to St. Pete, and he and Daniel just went nuts. They had this amazing bond, and they worked at all kinds of different things. Mostly, it was bringing Newton and Leibniz together that made their work happen. Newton had said F equals ma, remember that one? And he thought about universal gravitation, so he had the law of gravity. All this stuff about dynamics and mechanics that Newton understood really well, combined with Leibniz's approach to calculus, this became a powerhouse for them to get all kinds of results. Did I list any of them? I think I did. No, that's the end of the slides, too. So, no, it's not. There's this quote from Straub, I want to mention. So, Straub really liked Bernoulli. Dan. So, Bernoulli's active and imaginative mind dealt with the most varied scientific areas. Such wide interest, however, often prevented him from carrying some of his projects to completion. It's especially unfortunate that he did not follow the rapid growth of mathematics that began with the introduction of partial differential equations in mathematical physics. So, guess who did partial differential equations?
But
That would be Euler.
his cousin.
And the French mathematicians, the Napoleonic era. No, Euler's part of that. Do you know what partial differential equations are?
Isn't that like the heat equation?
The heat equation or the Laplace equation is one. So, you know what differential equations are? You have the derivatives of a function and maybe the function, maybe multiple different derivatives combined into some combination equals zero. Or, you move things around so that maybe the second derivative is equal to a constant times the function, things like that. That's a differential equation. Partial differential equations is just saying, well, take a function of multiple variables, and you have partial derivatives. Write down some relationship between those. Does that define a function, or does it lead to something that's contradictory? There's interesting questions. The heat equation, for instance, it's called that because it describes the way heat flows in a uniform material. So if you think about like a metal plate, and you put a blowtorch under it, heat it up, maybe put a couple of blowtorches under it in different spots, so you get spots of heat, right? Now take the torches away and watch that heat dissipate, flow across the surface. There's an evolution going on there as the hot spots fade away and the whole plate eventually becomes uniform in temperature. So that evolution is governed by this partial differential equation. That's what Laplace's equation. Anyway, I was trying to finish reading this. Nevertheless, he assured himself a permanent place in the history of science through his work and discoveries in hydrodynamics. His anticipation of the kinetic theory of gases, a novel method for calculating the value of an increasing assets. So, he went over to the dark side and did financial math.
So he did accounting?
No, financial math. Really, more than just accounting, figuring out how to increase assets. And the demonstration that the most common movement of a string in a musical instrument is composed of the superposition of an infinite number of harmonic vibrations. What is that saying?
The guitar string vibrates.
Yeah, remember when I brought the guitar in and we played the fundamental tone, which basically has the string waving just with its endpoints fixed. But when you touched it in the middle and plucked it, you get the first harmonic where the waveform is kind of a pair of things that look like that. So while this side is going down, this side is going up, but you still get a double the frequency note there. Well, there's more harmonics than just the second one. I think I tried to play for you the third one. I'm not such a good guitar player, so did it come out? Were you able to find the third harmonic? That's where the string vibrates so that there's like two nodes and looks kind of like that if you put it under a strobe light or something so you can see it moving. Well, there's infinitely many of those things. So really the string is vibrating to a certain extent in all of those modes at once. Now, that's not, it's not fair to think about them all being the same size. You would have the fundamental thing much more than the first harmonic, and that much more than the second. I feel like we should call this the 1, and this 2, and this 3, and the rest going down. So the contributions of these continuing harmonics are smaller and smaller and smaller. You know what? That's an infinite series again, isn't it? The difference between that infinite series and the infinite series we're used to is it's not in terms of x. It's in terms of sine of x. So you'll have something that looks like this. A coefficient times sine of 1 times x. And the sum is infinite. That kind of thing is what's the basis of what we now call Fourier analysis, but it was actually Daniel Bernoulli that started it.
So isn't that just infinite because sine always oscillates?
Second.
Isn't it just infinite when sine is always oscillating?
Well, it's not infinite because of these numbers. So this one starts, the first one of these might be 1, but the next one a half, and the one after that a quarter. And if these numbers go down in like a geometric series, then the contributions of all the ones way out there become nil. Not 0, but so small that they don't make the thing blow up to infinity. But you're on the right track if you think about the question you raised is really, does it converge or not? Is this just going to be infinity?
I'm guessing square root of 2.
No, it depends on what numbers are those coefficients. And you can get different things based on how you adjust those coefficients. It's really interesting. The Fourier analysis is it's a pretty remarkable area of math. But I could give you an example. Suppose I wanted to build a function that you may not believe that you could do this. Could you create, using sine curves, a thing that looked like that? Square tooth, a square wave. Can that happen with sine curves?
Yeah, I know. I've seen it.
You've seen that?
Yeah.
Like on an oscilloscope or something?
Not just on sound waves, like
Yeah.
squares, something convert sine wave.
So you can, if you have like a good synthesizer, one of the options would be to create square waves. Let me try to show you how to build a thing like this up out of sine waves. First, get really approximate. Just build a sine curve that mostly fits it. Okay? That's like your fundamental tone, right? Now, away from that sine curve, we need to deviate a little bit. We need to get up into the corner some and get rid of those peaks some. So you build a second sine curve around the first curve that has, oops, what did I do wrong here? Oh yeah. Yeah, my picture wasn't as good as it should have been.
That's good enough. We know where you're getting at.
You know what I'm getting at? Okay, good. So, and then that was the fundamental one, and then if you notice, it was not the next guy, it was the third one. I needed to get up, down, up happening in there around that, to get closer to the square. So what you do actually is make a sub n 0 for all the even ones, and I believe it's a geometric series for the odd ones. So it'll be a sub 1 would be 1, a sub 2 equals a sub 4 equals a sub 6. Those are all 0. Or maybe I'll write this with 0 equals that, and then I can have to be honest about that knots there. And then a sub 3 would be a half. And a sub 5 would be 1. And so you make it converge by making these odd coefficients head down towards 0 rapidly enough. If you make it fit closer and closer to the square wave by eliminating the even coefficients, you can create a function that looks just like a square wave out of these things by appropriately choosing the base event. That I'm doing this just sort of graphically right now, but figuring out those coefficients is what Fourier analysis is all about. that's probably a good place to stop. Because I'm out of slides and we're 5 minutes early, sorry about that. I usually do time this, I usually have it like there's extra.
Yeah.
Yeah.
Maybe we didn't ask us good questions.
Did I talk to Pat?
Yeah, I think.
Did I have most Pat?
Will you take your time to get your papers?
No, I have.
It's okay if you don't.
Oh, I guess what I do have back. Except they're not in this bag that I got with me.
Any, but
I think.
No, they're in my computer bag. It's Friday, it'll be Friday. Yeah, I have a quiz, and I have a, did I have a quiz that I put in the chat?
Hell yeah.
So I've got that, and I've got biographies and something else. Prior to the biographies. Some people's Babylonian trigonometry. I'm not sure if I can myself. We'll do that Friday.
So I never hate Bernoulli's. Why do they all go by Bernoulli? Why didn't they do something to differentiate each other? That way it's easy to keep track of.
That is funny. Do you change your name just because you've got an annoying cousin who does the same kind of work as you? Who happens to have the exact same name as you?
That's not annoying because of this.
My thing is, why do
You know, they're all such attention-seeking, greedy people. Maybe they were just
That
hoping
was-
that
that
they
was
would all
really-
just kind of be brought.
Wait, I just want to make it clear, that nasty personality thing seems to be limited to the first generation. One of the first generation guys was the one that fought with his own son, but after that, they got to be much cooler. Yeah, okay, all right. See you later.